I finished the slides 5 minutes ago, and actually, strictly speaking, 2 minutes ago, but you know, so they're fresh. Because I realized I had some code from that I first used in my Build Stuff talk last year, and I suddenly thought, I need some new code here. So I will put that one in. Let me just check I use the right code. Just a moment. I'll be with you. The joy of versioning across PowerPoint. Okay. And at some point, we should actually have a black screen come up. Is that? Yeah, that's the black screen. Oh, there we go. Something's happening. No? No. There we go. Now something's happening. Okay. Good. Right. So, this talk is that font about the right size? This talk, I was thinking about a talk last year. I realized I had been referring a great deal to papers, ideas that have been around for a long time. And a couple of years ago, I did a talk, old is the new. I didn't do it here at Build Stuff, but I set myself a constraint. Can I talk about modern concepts simply by referring to papers and ideas no later than the 1990s? And in doing so, I was reading around a little more, going back over references that I've often referred to, and realized that there were a number of them that date back to 1968. And then at which point I realized, in a moment of arithmetical insight, that we were coming up to 2018, 50 years on from 1968. And I thought, you know what, there's a 1-year opportunity to do a talk. Okay, so I've been doing this talk, and it's evolved slowly as the year has gone by. Just looking back at some of the ideas, I'm not going to say, oh, we had it all worked out in 1968. I'm absolutely not saying that. But I do want to say that perhaps you don't know how old some of the ideas you're dealing with are, and that many of the things that we think of as new are anything but new, and that many of the things that we are ignoring at the moment, perhaps in our industry, are the things that we will look back in a few years' time and go, oh, yeah, that was good. So it's really more a case of we need to pay a little more attention, and to pay attention to our own history. As software developers, we're not very good at the sense of we have a history. People often say, oh, software development is a young profession. No, it isn't. It is older than everyone in this room. Okay? I know of professions that actually are younger than software development. There are lots of them. Okay? It's one of those conversations where you talk to somebody and they introduce themselves and, yeah, what do you do? And they say something and you realize, I have no idea what you just said, but apparently it's a job, okay? So, that's 1968. Other people remember it for different reasons. 1968, there was a lot going on. Now, how are we going to get back to 1968? We are going to use a time machine. Fortunately, Facebook has given us one. Foolishly, I tried to send Facebook some feedback a while back. Your feedback will be used to improve Facebook. That has not yet happened. Okay, I'm just putting that one out there. Thanks for taking the time to make a report. How much time? This has taken us all the way back to 1969. Okay, we'll walk to 1968 from there. It's just a short distance. So clearly there is, this is before the beginning of time. The beginning of time is the 1st of January, 1970. And clearly there's a minor off by one error here. So what's happening in 1968? One of my favorite artists, Jimi Hendrix, was having one of his peak years, 2 major album releases, absolutely brilliant stuff. Led Zepp formed. In fact, we could stop the talk right now because this is already good. However, it was also a time of political change, political upheaval. Paris riots, the Prague Spring, Civil Rights Movement, the Fair Housing Act in the US. Sadly, the assassination of Martin Luther King. But we also had a really new perspective. This was taken Christmas Eve, 1968, Apollo 8. This is the famous image, Earthrise. This is the first time that humans had been out to deep space. People often think of space as being far, things like the International Space Station as being far away. They're not. They're really close. If you drew the Earth and then you drew where the ISS is, you wouldn't make any. You couldn't see it. Deep space is seriously far away. So there is this notion of humans had not, with their own eyes, had this perspective before. And so there's kind of something there that we should look back. And somewhere down there, there's me. I'm the little one there. So, but I was born before 1968, but that is a picture of me in 1968. The world was black and white back then, just for those of you who are too young to realize it. It's, Dad, when was color invented? Well, we didn't invent color till the 1970s, son. We all walked around in various shades of gray. On the TV was the 3rd season of Star Trek. Yeah, exactly. It's just like, yeah. And to this day, I am one of those people who cannot hear people talk about enterprise software without thinking. It was also the year in which my favorite film was released, 2001: A Space Odyssey. Actually, from a typographic point of view, there's a number of things that are interesting about 2001. It uses the Gil Sans font, which was developed in 1928. And unusually, if you look very, very closely, the zeros are not 0. They are O. That's one of the things that makes the title look so simple and so bold. Interestingly, it was also the same font that was used on the original. This is actually the PDF, which uses Futura font, which is slightly different. That was 1927. But the original font, so maybe I like typefaces and fonts, okay? But Software Engineering Conference in Garmisch, the NATO Software Engineering Conference. This was interesting because this was a group of people getting together and saying, you know what do we know? How do we take this forward? And this is a massively influential report. Now, the interesting thing is that very influential, but people often don't read it. And thanks to the internet, you can pretty much read anything that's ever been written. So I did take the opportunity last year to sit down and read this. It's a bit of an eye-opener. Now, as an example of the misunderstandings that people often say, they say, oh, that conference, that caused all the problems. And we had, so in Pete McBreen's book, Software Craftsmanship, he positioned this book, it was published, 2002? He positioned this book in opposition to what he perceived as software engineering. And he said, oh, software engineering was invented to tackle the problems of really large NATO systems projects. There's only one problem with this statement. It's completely false. Apart from that, it's okay. That's not actually at all what happened. It was the NATO Software Engineering Conference, but it was not about NATO. It was NATO-sponsored. That's a completely different thing. Yeah, it's a little bit like when sponsors sponsor beer at conferences. That doesn't mean that those sponsors are actually producing beer. Okay, there's a subtle difference. The term software engineering was popularized by this woman, Margaret Hamilton. She created it. Sort of rather nice tie-in with the images we've already seen. She was involved in the Apollo program and led a team that did some fairly serious software from a modern perspective. Basically invented some concepts of fault tolerance that are still in use today. And they even included a moment that her well, they obviously didn't list this, but in the recent film, First Man, there was actually one of the key events, which I was very pleased they included, that her software was responsible for kind of saving the landing at one point. I began to use the term software engineering to distinguish it from hardware and other kinds of engineering, yet treat each type of engineering as part of the overall systems engineering process. I think this is very interesting because she treats it as a very holistic thing. It's part of a bigger picture. It is not it's simply a discipline on its own. We're trying to build something that is far larger. She also wanted to use this term to make sure that the software people were being paid attention to. Because back then, there was the notion still that hardware was your major cost. That had actually already passed a couple of years before. People had started observing this in the early 60s, that actually, maybe maybe the software development, maybe programmers are actually more expensive than the hardware in the long run. This was already an emerging observation. But back then, people sort of said, oh, software, that's just a detail. People still say that. The term was even gaining popularity. This is 1966. This is the chair of the Association of Computing Machinery, ACM. We must recognize ourselves, not necessarily all of us, and not necessarily any one of us all the time, as members of an engineering profession, be it hardware engineering or software engineering. So sometimes people say, oh, well, the Software Engineering Conference in 1968 invented the term. This is very, very far from the truth. And it has also nothing to do with NATO. Now, other things were happening in 1968. 1968, Fall Joint Computer Conference. This was a bit of a landmark conference. Here's a listing of the proceedings. Most of these things are not necessarily landmark moments, but there is this one. This one's interesting. A research center for augmenting human intellect. Douglas Engelbart, W.K. English. This included what has since become known as the mother of all demos. This included little things, crazy ideas for how we might interact with computers, maybe using window systems or hypertext, word processing, actually interacting with a machine, using networking, dynamically linked modules, use of mice, real-time editors, version control. Okay, so this was not exactly what we call widely available, but pretty much 1968 had a fairly good idea of the future. It was also the year that the A-star algorithm was invented, which is an improvement on Dijkstra's pathfinding algorithm. The reason that matters is because it's used in most games today. Okay, so really 1968, hell of a year. So let's go back to this. So these people were to blame. These people who went to this were to blame for all the problems that we now have. Is that right? Waterfall development, all of this kind of stuff, plan-driven development as it's been reframed. Actually, this is quite a long way from the truth. Here's a quote. I've only been 7 months with a manufacturer, and I'm still bemused by the way they attempt to build software. Feel free to relate this to your experience. They begin with planning specifications, go through functional specifications, implementation specifications, etc., etc. This activity is represented by a PERT chart with many nodes. If you look down the PERT chart, you discover that all the nodes on it, up until the last one, produce nothing but paper. It is unfortunately true that in my organization, people confuse the menu with the meal. This was already a criticism. Folks in 1968 didn't think of themselves as necessarily being at the beginning of something. They already regarded the profession as old enough that they had war stories, that they could already see some of the problems. And of course, in the proceedings, there's not everybody is saying exactly the same thing. There's a diverse opinions, just as you expect with any group of people. But this theme keeps recurring. The most deadly thing in software is the concept, which almost universally seems to be followed, that you are going to specify what you're going to do and then do it. And that is where most of our troubles come from. Honestly, you could take the year off this and quite happily put this into any document, any blog post now. And then the profound insight from Andy Kinslow. The design process is an iterative one. Again, 1968. Now, we can obviously question what happened after 1968. Well, the 1970s. Disco, flares. I don't know what the problem was, but clearly we lost something because these ideas were all to play for. They were there, they were available, but history took us down a very different path. Now, what is interesting is going through this document, an iterative is not the only thing that pops out. Up until reading that document, I had thought I had traced back the term unit test to the 1970s. I thought it had originated in the 1970s. But here it is used freely. Okay, so that's clearly there. The term middleware, I had thought was the early 1980s, possibly the late 1970s. No, it's in there. Melvin Conway and Conway's law get referred to. Christopher Alexander, the guy responsible for design patterns, he gets referred to. We'll come back to him later. Acceptance testing, layered architectures, modularity. This is all importantly, a lot of people think that modularity was an idea of the 1970s. They normally cite David Parnas's paper from 1972, and that was a very important paper, but the idea was around of some kind of modularity, not necessarily the criteria he described, information hiding. That was kicking around in the 60s. Declarative approaches, in other words, these are all there. They all get a mention. So let's go back to Christopher Alexander, who in the 1970s developed a system of ideas, which we now refer to as patterns. And I'm kind of partly responsible for being in the patterns community. The architecture metaphor had already emerged. We can actually take architecture back a couple of thousand years. Turns out that Vitruvius, a Roman architect, came up with 3 really good and useful properties that we want in our building architectures, but also actually in our software architectures. Firmitas, firmness, robustness, strength. Utilitas, utility, usefulness. How useful is this software? How useful is this building? Venustas, if you knock off the last 3 letters, Venus, the goddess of beauty, it must be beautiful, it must be aesthetic in some way. So these are all things that it turns out we care about. And I often point this out, when people talk about patterns, they often end up gravitating towards this pattern. Well, actually, I don't mind if they gravitate towards this one. Well, this one's mine. Singleton is a whiskey. And if you are thinking about, anybody in your project is thinking about adding a singleton into the code, bring a bottle of this stuff online. You can buy it, okay? It's much better for your code, okay? If you have a few shots of this, you relax, you calm down, you just go, you kind of get that gentle fire in your mouth, and you go, you know what? We won't put a big global variable in our code base today. That's a really bad idea. Globals were already recognized as a bad idea in the 1960s. Now, the reason I've gone down this patterns rabbit hole for a moment is because a few years ago, while everybody was getting into manifestos, I realized patterns did not have a manifesto, and I was at a workshop, and I suddenly thought, you know what? Maybe if they did have a manifesto, what would it look like? And that is very much what drove me into this talk as well. We are uncovering better ways of developing software by seeing how others have already done it. Let's actually go back and look at our history. This idea of patterns and also the knowledge of the past was captured by Brian Foote, a member of the patterns community. Patterns are an aggressive disregard of originality. Let's go and look at things that people have already done, because they might have stuff, they might know stuff that might be useful to us. And then we can go and do the new interesting stuff, rather than reinventing the wheel. And if you're going to reinvent the wheel, at least make it interesting. So there's this question, what do we mean by engineering? Glenn Vanderberg gave a really good definition a few years ago, which kind of ties in with that. Capsule definition of engineering, independent of any discipline, as you're likely to find, the set of practices and techniques that have been determined to work reliably through experience. Now, this is an interesting one, because sometimes people say, well, software engineering is not like the other engineerings. And people often focus on bridge building and stuff like that. It turns out electrical engineering is quite different to building bridges. It turns out all of the engineerings are fundamentally different from one another in one way or another. But the one that does unite electrical engineering, civil engineering, and all the rest is this notion of physicality. They are physical. And people often say, well, if software engineering is engineering, then surely the manufacturing, the creation stage, is what we would normally call construction, and we actually see it in our language. We talk about the idea of people building software, but it turns out there's a misalignment, because there's another word, if you might think about it for a moment, your build process. Turns out your build process is automatic. Your build process doesn't really involve people, except when it goes wrong. It turns out that we solved the manufacturing problem, we solved the physical logistical problem a very long time ago. That was actually the 1950s. What we do is we spend our time designing. The manufacture happens within the compiler and the build system. That is the manufacturing stage. It's not the bit where people are writing code. That's not manufacturing, that's designing. We've got a kind of an off by one error when we've tried to apply physical engineering metaphors. So what do those guys in 1968 have to say about this? Well, they were very clear about this. Peter Now and Brian Randall, who were the editors of the proceedings, the replication of multiple copies of a software system is the phase of software manufacture which corresponds to the production phase in other areas of engineering. In other words, they say, right, we've already done this. It is accomplished by simple copying operations and constitutes only a minute fraction of the cost of software manufacture. They were very clear that the metaphor was not aligned with people doing this is equivalent to the production phase in physical engineering processes. It was all there in black and white. They were very aware of this. Now, I'm going to go back to Christopher Alexander because there was something that I did not appreciate. Gesundheit. So this is my copy of Notes on the Synthesis of Form by Christopher Alexander. Turns out that prior to his work on patterns, in fact, building up to his work on patterns in the 1970s, Christopher Alexander wrote this book, published in 1964. Now, I read this book a number of years ago, and that's my copy. It's kind of got a particular aesthetic that no longer appears in books. People don't publish books like this anymore. They probably use nicer, more modern fonts, but there's a kind of robustness to this, a sort of a joy. If you ever see, this is the kind of book you find in secondhand bookshops that's really nice. It's just like, oh yeah, this is a proper book. And I'd read this book, but what I did not realize is how influential it was in the 1960s. Because I'm reading through the software engineering proceedings, and they start referring to Christopher Alexander and the synthesis, this stuff, the synthesis of form. And it turns out it was a very influential work, a long way outside architecture, building architecture, where it originated. He was talking about design of anything. And it actually influenced a number of folks in the software community at the time in a way that I hadn't appreciated before. And we can start seeing why. He starts talking about ideas that have become second nature to us. We may therefore picture the process of form making, the process of creating a structure, as the action of a series of subsystems, all interlinked yet sufficiently free of one another to adjust independently in a feasible amount of time. It works because the cycles of correction and recorrection, which occur during adaptation, are restricted to one system at a time. And he kind of draws this nice little diagram showing, inside, outside, and connections, and so on. He's talking about very much that how do you build an architecture that deals with change? Now, it was only when I was reminded of this that I suddenly thought, wait a minute. It turns out that everybody was really into drawing circle diagrams as well in the 1960s. We shifted to rectangles in the 1990s, just to show you how time advances. So here's another one that uses, you see, I had not made the connection until I revisited Notes on the Synthesis of Form. And you're going like, what the hell's Kevlin showing here? Why is this important? Because this is from Melvin Conway's paper, and Melvin Conway did a keynote here at Build Stuff a couple of years back. How do committees invent? This is the paper from which Conway's law dates, and that was a 1968 paper that was referred to in the software engineering conference. Okay, this idea crazy idea, hey, maybe the way that people communicate with one another will influence the software they produce. Oh, don't be stupid. Well, of course they will, because software is an informational thing, and how people communicate and organize themselves informationally is going to clearly have some kind of social influence and therefore structural influence. The basic thesis is that organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. So if you want to change the ease of your architecture, then you need to change the communication paths. Now, this is the bit that people often quote this bit, but they never quote this bit, which is the next bit in the paper. We have seen this fact has important implications for the management of system design. A design effort should be organized according to the need for communication. Now, this is kind of interesting because if we think about how do people organize development efforts, in some organizations, people organize development efforts based on who's available, so availability. In other cases, we talk about in terms of skill. And he's suggesting here perhaps the way that people talk to each other might also be a consideration. Yeah, it's kind of obvious when you say it. And that's the problem with a lot of these. They're kind of obvious when you say it. It's like, well, how do we miss that? Even somebody as obstinate and purely mathematical as Edgar Dijkstra acknowledged this. I believe that both the total density of information flow necessary between groups, of course, because it's Dijkstra, and if you haven't read any Dijkstra, this is how he writes, and the percentage of irrelevant information that a given group gets can be greatly reduced by effectively structuring the object to be constructed and ensuring that this structure is reflected in the structure of the organization making the product. You know what? I'm with Melvin on this one. His words were better. But Dijkstra got there. There is a truth here. And it's an important truth. And this observation, what I find interesting is these days we have a lot more focus on things like code analytics. So Adam Thornhill's classic, Your Code is a Crime Scene, he looks into this. This idea that your organizational structure will influence your architecture, we've now seen in action many, many times. And as he says, even though Conway formulated his law around the initial design of system, the law has important implication for legacy code as well. And people were already beginning to experience the joy of legacy back then, but perhaps they hadn't had the full joy of legacy that we now have. Because, you know, I visited a client 3 years ago. I ran a workshop for them. So I go to a lot of places, and people say, "Oh, our legacy system." What do we mean by legacy? Normally, it means something to do with old. Normally, it definitely means code I did not write. That's everybody's kind of like personal, private definition of legacy code. Code somebody else wrote. Or code that I'm not prepared to admit that I wrote. And a lot of people, you know, I go to a number of companies, they say, "Oh, we've got this legacy code base." And sometimes the legacy is 3 years old. Sometimes it's 15 years old. Sometimes it dips into the late 20th century. This client has code that predates the 1968 Software Engineering Conference. They said, "Oh yeah, we got some code that goes back to the 1950s. Oh, fortunately, I did not see that. You know, I think that would be one of those things that you could never unsee. However, if we're talking about legacy systems, I'm going to present, I think I might have showed this one before, my favorite legacy system, Stonehenge. It's a computer. It's a big computer. And a lot of people look at it and go, "What does it do?" And it's just like, yeah, you see, that is it. That's a legacy system right there. What does it do? How does it do it? How did they create it? These are the questions that everybody comes to when they see the legacy code base. How did they build that? Why does this thing? Well, we don't know. What was the reason for building it? Those people are lost to history. We have no idea. But twice a year it produces a result, and we just hold on to that. Now, the reason I'm showing you this is not just the legacy, but I've thrown some Latin at you. Hell, let's do some Greek as well. Monolithos. Monolith. One big stone. Okay. And people say, "Ah, we don't want a monolithic architecture. We want this. We want elegantly arranged stones." Yeah, this is where my youngest son was, I don't know, he was about 5 or 6 when he did this one. Yeah, I was very impressed with his choice of Japanese aesthetic, just like a bit of seaweed on the top. And everybody imagines that their architecture is going to be like this. And they go, "Oh yeah, this is beautiful, partition these small stones." And we see that Doug McElroy had this kind of perception as well. So he was writing in the 1970s when he wrote this. This is the Unix philosophy, write programs that do one thing and do it well. Write programs to work together. It's a very simple philosophy. We're still struggling with it. But when people normally look at this, they often think, "Oh, Kevlin's talking about microservices." And if that makes you feel good, yes, Kevlin's talking about microservices. Yeah? If you're going, "Yep, that's right, fine." So I'm really talking about any modular approach, but it turns out that, you know, whether we're talking about component-based development, object-oriented development, any kind of concept of modules. But what I find interesting is digging through the 1968 proceedings was this. This was slightly unexpected. Define a subset of the system which is small enough to bring to an operational state, then build on that subsystem. Now, what is interesting here is he's not simply talking about modularity in the way that people typically talk about modularity in terms of information hiding. He's saying operational state. That's a very important difference there. This should work. It should be able to run on its own terms. Strategy requires that the system be designed in modules, which can be realized, tested, and modified independently, apart from the conventions for intermodule communication. So I'm not going to say David invented microservices, but I'm going to say that what we've been doing is repeatedly rediscovering some of the same principles. So what makes microservices meaningful now that perhaps would not have been possible then? In fact, honestly, microservices 15 years ago would have been a ridiculous thing. The reason is because this is the big change, because sometimes people say, oh yeah, but things have happened since 1968. Look at my editor. Look at my, I can run multiple operating systems on my platform. You've got this kind of like virtualization all the way down. I can do all of this. And I've got a screen that is this big. It stretches to the horizon. And you look at somebody and you say, and you know what we call that? We call that innovation in hardware. It is not, I repeat, not innovation in software. To be precise, what we're talking about is the fact that there's, if you like, software is this idea of what can we do? We could do this, but performance in the physical world will prevent us. What has been happening is that hardware has allowed us to fulfill these dreams of windowed systems and awesome editors across large screens. That's the hardware people we have to thank for that. But just please don't tell them that, because they get really big-headed. But this is the point. That's the key thing. If you try to run this on the operating systems and platforms of the 1960s, people wouldn't have even laughed at you. They'd have left a long time before that, because it wasn't going to work. So what we're seeing is how these ideas were there, but now we're in a position to take advantage of them in a way perhaps that we weren't able to before. But often people say, oh, microservices, and assume that magic happens. There you go, standard microservice architecture. Just because you're breaking stuff up doesn't mean it's going to work automatically and become beautiful. Alan Perlis, he was present at the 1968 meeting. He was the winner of the first Turing Award. In the long run, every program becomes Rococo. If you're not quite sure what Rococo is as an art or music movement, it kind of makes Baroque look minimal, then rubble. So he anticipated modern architectures really very well. He also made some other observations which I think are valuable. A software system can best be designed if the testing is interlaced with the designing instead of being used after the design. Wow, that's a radical idea. Instead of leaving it all to the end, why don't we do it while we're going? It's like, oh yeah, that's a crazy idea. Yeah, that's such a new-fangled agile idea from 1968. In fact, there's quite a lot on testing in there. And again, there's lots of different perspectives, but this one keeps popping up. Now, I thought, let's do some actual code. So I'll pick on an example I normally use. I run a page that's on language and words on Facebook, Word Friday. And a while back, I did one of the words I put up. I love this one, biquinary coded decimal. If you can ever drop that casually into a conversation, because I do know, somebody contacted me a while back, they said that they tried to use some of the words that I put up in a conversation, just see if they could sneak them in. If you can get that in a conversation, I will buy you a drink. Not a conversation, not let's talk about biquinary coded decimal. What is that? No, that's not a proper conversation. Just actually casually drop it in there along with everything else. A system of representing number based on counting in fives. Who knows where that could have come from? I have no idea. With an additional indicator to show whether the count is in the first or second half of the decimal range, whether the number is in the range 0 to 4, 5 to 9, or 1 to 5, 6 to 10. The system is found in many abacus systems. A proper abacus system, rather than ones you have for your kids, doesn't have 10 beads, it has 5 beads and 2 beads. That's how they're structured. But don't give that to your children, because it'll really mess with them when they're trying to learn to count. Unless you want to bring your children up fluent in biquinary coded decimal, in which case I would like to see the write-up of this social experiment when you have that ready. Even early computers, a lot of the early digital and electro-digital computers, the 1940s and 1950s, actually used biquinary coded decimal until somebody said, what about binary? That's crazy. Yeah, but this is fun. And one of the classic systems is Roman numerals. Okay, that's biquinary, which means we're going to do the Roman numeral problem. So there you go, 1968. So I thought for this, I'm going to pick on a language. I gave an example of code using this language last year, but not everybody was here last year. I thought I'd do something different this year. Let's do Roman numerals. So what I'm going to do is give you some code here. Yes, I've got spaces in my identifiers. That's cool. Got string type. Skip just means no op. The language in question is Algol 68. The clue is in the number. Although, strictly speaking, the revised report was 1974. But Algol 68 is one of the most influential languages that you've either never heard of or never used. Massively influential. Even little features like int. Everybody else in the 1960s was busy writing integer. But those folks in the Algol community, they'd had enough of that. Just no. Boolean? No. Bool. Character? Oh, no. Char, thus starting the war. Is it char or is it car? I leave that to you to resolve. The words union, struct, short, long, the whole short-long concept, that all came from Algol 68. Void, this is all there. These are all the words, and there's a lot of other ideas floating around in there as well. So, other things that are worth noting. Algol 68 came with a built-in assert, which languages often don't have or don't get until much later, but this was the first language to have it properly built in. So let's have an implementation. Let's assert the Roman numerals of 1 is I. Let's have a very simple implementation. There you go, I. I don't have a return statement here because Algol 68, it's kind of interesting. It's a procedural language. Normally people use the word procedural to mean, oh, that's bad. Actually, it was a really good procedural language. It basically understood that procedures are for manipulating values. Statements are simply things that yield values. So this idea that everything can yield a value was actually present in procedural programming. We often attribute that solely to functional programming, but the idea is this yields a value. So all expressions can be made into statements, and all statement concepts can be used with inside expressions. Algol 68 was the language that gave us the concept of orthogonality, the very term that was used to describe it, design, and had a very strong influence on the C family, and everything's descended from it. Okay, we obviously need to have a little more code here. So we'll go for Roman numerals of 5 is V. Oh, okay, so here's an implementation. If year is equal to 5, then V, else I, phi. Now, if you've ever wondered where the whole if and phi thing came from, if you're using bash or related shells, it came from Algol 68. Indeed, Algol 68 was influential. Didn't it just influence the designers of C? It also influenced a chap called Stephen Bourne, he of Bourne Shell. Stephen Bourne was so taken with the idea of Algol 68 that he decided to write his C code for his shell using macros in C that made the code look like Algol 68. And this is how the International Obfuscated C Coding Contest was started. Because when you open a file that ends .c, you're expecting to find C code and C syntax. You open it up, it's going like, what the hell is this? And people go, yeah, okay, that's fine, but, you know, Stephen, really? So yeah, it was basically that idea of how can you abuse the preprocessor and the language became a thing. Okay, and we've never really looked back since because we can't see anymore because we're blinded by the code. So let's move on a little bit. Let's move on. Let's assert some more. So yeah, the elif, all of this structure is there. And so notice I've got no return statements here. It's the result of the expression. Now, obviously, we can generalize this one up. Now, the way that I've approached the Roman numerals problem, a lot of people approach it by what I consider to be a non-domain approach. They often approach it by saying, 1 is I, 2 is I, 3 is I. Take a moment, look at the domain. The domain is characterized by numerals. It's called the Roman numeral system, so let's actually explore the numerals. Now, when we recognize this, we end up with a lot of code like this. You can see if you can continue this, this will turn into enterprise code. We referred to enterprise earlier on. But, you know, perhaps we recognize that perhaps there's a more declarative way of doing it, a table lookup. So here's an interesting thing. There we go, struct in action. This is an array of structs that take value and a letter, and here is a way that I can construct it very easily. This idea of being able to have free and easy literals of all types was also embedded into Algol 68. Turns out a lot of languages took a long time to get there. Of course, I need to drive this, so I have to throw in a little bit of extra code. Didn't use do or done, it used do and odd. It was relatively consistent with that. Anything else I want to point out here? It's a procedure called Roman numerals. Takes a year, returns a string. So there was a string type in the language. Yeah, there's no dot notation. Use of. Instead of mapping entry dot value, it would be value of mapping entry, and a standard kind of colon equals assignment for the time. So this is all fairly straightforward. Algol allowed you a number of options. This is one of its weaknesses. It sort of said, oh, well, you know, this is one way of writing it, but there's lots of alternative ways of writing it. That was a weakness in the language. But you could replace the begin and end with parentheses. Now, it turns out that it was not unique in this. There were a number of languages in the late 1960s that decided that instead of typing begin end, perhaps we should use parenthetical type things. And so around the time, 1967, BCPL, which was a precursor of C, used a 2-character opening form. Algol chose to just use single parentheses. You can see they're being used a lot, possibly a little too much in the language. But we also have to remember that it's a hardware constraint. Remember, I said it's all about the hardware. Keyboards did not generally have as many exciting symbols as we have today. Okay, and you know, and certainly I always get this whenever I go to Scandinavian countries. Where is the curly bracket on the keyboard? You know, you spend a little bit of time hunting that one down, and eventually, yes, found it. I can open a block. So they hadn't discovered the curly bracket back in 1968. That was a discovery of the 1970s. So yay, 1970s, curly brackets. Okay, so let's do some more. I'm gonna go wild with the table-driven approach, and I'm going to create my testing framework. Instead of just doing raw asserts, what I'm going to do is I'm going to make my testing framework declarative as well. Decimal positions correspond to numerals. 1 is I, 10 is X, 100 is X. And quinary values correspond to numerals, 5V, 50L, 500D. Okay, so I've got that. I've got a test driver, which I'll show you in a moment. But if you start looking at all these parentheses, you start thinking this begins to look a bit like Lisp. Now, Lisp is a language of the 1960s. Sometimes people say it's a language of 1950s, but the first working compiler or interpreter for Lisp appeared in 1960. So up until that, it was just paperwork and ideas. This is my copy of the Lisp 1.5 Programmer's Manual. You can find the PDF online if you want. It's a fascinating read because back then you had to tell people how to build your language because there was certainly no internet, but also there was no standard architecture. So you described, here is how to build a Lisp machine, basically. Absolutely fascinating and surprisingly readable. Yeah, it's a really interesting education to see the freeness of the thinking that they had. So we'll go back to that, and I'll create a test driver, test Roman numerals against Roman numerals spec. I'll call this the Roman numerals spec. I've got all my little pairs of values. I've got some structures here. Algol didn't call them types, it called them modes of access. Resizable arrays. I've got some code. I'm not going to spend any time on this. The only thing I want to rest on for a moment is to notice plus colon equals. If you take away the colon, yes, this is where the plus equals operator came from, Algol 68. So there's a few features there. String concatenation was built in. So there's a lot of these features that were fairly standard. Nice example down here of being able to use an if statement inside an expression. You didn't have to have the Elvis operator, no question mark, colon, or anything like that. It was a regular language design. There's a certain irony that in the 1960s and 1970s, people said that Algol 68 was too big to implement. The Algol 68 spec is actually smaller than JavaScript. It's smaller than Java. It's smaller than modern C. Our idea of what is big has changed. So I have actually tested all this code. There are free interpreters and compilers available on the internet because there's always somebody who's crazy enough to implement it. That is the joy of a connected community. You can always find the person whose hobby it is to go, I'm going to build that. Multiples of decimals are additive, so we got a bit more code there. While loop, nothing special about that. Then non-multiple decimals are additive. Turns out that we don't really have to we simplify the code, and then this all works perfectly. Numeral predecessors are subtractive. We don't have to change the code there. Just the lookup, and then we're done, basically. That's it. Everything is there, and what we've got is a very test-driven 1960s style. Now, I'm not going to say that test-driven development existed in the 1960s. You have to wait till the 1970s for that. This is Alfred Aho. We instituted a rigorous regression test for all the features of awk, which is a pattern-matching scripting language that is standard on Unix. This was the 1970s. Alfred Aho, Weinberger, Kernighan developed it, AWK. Any of the three of us who put in a new feature into the language first had to write a test for the new feature. So they did it in what we would now recognize as a test-first approach. So, yeah, the 1970s did contribute stuff. Test-first programming and curly brackets. So we're doing well. So, Alan Perlis makes this observation. There's no such question as testing things after the fact with simulation models, but that in effect, testing and replacement of simulations with modules that are deeper and more detailed goes on with the simulation model controlling the place and order in which these things are done. As design work progresses, this simulation will gradually evolve into the real system. What are we talking about here? What we're actually talking about is an approach that was put forward by Brian Randall. These days, we'd recognize it as mock objects. They use the term simulation. They are talking about the idea of mocking, but from a very different perspective. This is also the period, this book was published in 1974, but it collects papers and essays from the late 1960s to the early 70s from Ole Johan Dahl, Edsger Dijkstra, and Tony Hoare. Dahl is perhaps best known for being co-creator with Kristen Nygaard of Simula 67. So Simula actually gets mentioned in the software engineering proceedings. It was where object orientation was effectively born. But when most people look at this book and they say, oh, structured programming, one of the first things they always think about, oh, structured programming, that's just about GoTo, isn't it? We don't have to worry about that anymore. Well, I've seen a lot of code where it turns out people are remarkably ingenious. Even without a GoTo, people are still embracing GoTo-based programming, but they do so in very weird and different ways. I mean, recently, a few years ago, we called it aspect-oriented programming, for example. Yeah, it keeps popping up, and there's some crazy stuff that people do with exceptions. But I'm pinpointing this one to this year because this is the year in which Edsger Dijkstra's famous GoTo statement considered harmful letter was published in Communications of the ACM. And again, this is something I mentioned in Word Friday. There's a concept known as a snow clone. Again, more vocabulary. This one might be easier to drop into a conversation. What is a snow clone? It's a cliched wording used as a template, typically originating in a single quote. For example, X considered harmful. These aren't the X's you're looking for. X is the new Y, it's X, but not as we know it. No X left behind, it's X is all the way down, all your X are belong to us. These are examples of snow clones. Phrases that people parameterize and they change and so on. GoTo statement considered harmful was one of those, and that's kind of its key origin point in software, was that letter in 1968. However, there is a curious thing. Digging through the history of this, it turns out that's not what Dijkstra wrote. Here's his original letter. A case against the GoTo statement. That's much more moderate. You know, GoTo statement considered harmful, that's kind of 1960s clickbait. Okay? You'll never believe what happened to this enterprise code when I used a GoTo. Yeah? Oh, I've got to click through and find out. This was actually the editor at the time, Nicholas Wirth. Nicholas Wirth was responsible for inventing the Pascal programming language. He was the editor. He changed the title of the letter. So this is kind of what he was talking about. And what a lot of people were focusing on at that point was this idea that we can structure things in a hierarchical fashion, decomposition. Alan Perlis, everything should be built top-down except the first time, which I think also shows us that even then there was this recognition that you can't do it perfectly. This whole idea that software development is a feed-forward process. It turns out that top-down is a great way of describing a system that exists, but you may not have created it that way. You normally only know what it looks like afterwards. Tony Hoare also had this observation. You cannot teach beginners top-down programming because they don't know which end is up, which I thought was very, very helpful. And again, there's this notion here that we often think of structured programming as just being about the control flow. But it turns out that that book that I mentioned, Structured Programming, also includes the last section, because people never read the last section, includes a whole load of advice on how to structure class hierarchies. It actually, from their perception, structured programming included object-oriented programming. It included data abstraction and data structuring. But people forgot that because many of the languages they tried to use, things like Fortran, did not support those constructs. So they just focused on the go-to aspect. What they were really focusing on was structure as a whole. We can actually see this idea of tree structures, concept hierarchies. The construction principle involved is best called abstraction. We concentrate on features common to many phenomena. We abstract away features too far removed from the conceptual level at which we are working. They're describing the inheritance construct. And this is this is the forgotten art, if you like, of all of these things. But this idea of decomposition and then composition also led to a paper from Doug McElroy. Now this was a memo from 1964. So this was exactly 4 years before the end of the software engineering conference. This is a memo, and in it, Doug McElroy observed, we should have some ways of coupling programs like garden hoses. Screw in another segment when it becomes necessary to massage data in another way. And this is the way of I/O also. This is the pipeline. This is the data flow architecture approach. This is where it all began. So these ideas were all there. If you're wondering about the Unix pipes, it took 6 years to find the pipe symbol on the keyboard. Okay, that pipe symbol did not happen until 1970. And that was Ken Thompson. But McElroy had said, no, this is a valid architecture, we should consider this. So I'll bring this to a close with the simple observation that everything has been said before, but since nobody listens, we must always start again. So I hope that has been useful, thought-provoking, maybe perhaps that you can look back at the history of an idea that you are currently employing. Go back and look at the history. See the silly mistakes they made, but also see some of the interesting things that we may have left behind. Ideas that you may not have reinterpreted or reapplied. But also with this, recognize that somebody in 50 years' time is going to look back to now and say, what is it that was almost obvious then, but we overlooked because we were so much in a rush to embrace the latest trend. Thank you very much.